It was a very long time ago that I first became acquainted with the observatory, and it's probably been the one of the most interesting and pivotal assignments and activities in my professional career. I first went to Arecibo as a graduate student in 1967. Was there for a couple of years, went away for a while, came back in the early 70s as a site director at Arecibo, was there for almost 10 years, and then rejoined the administration at Cornell. And even at Cornell, my portfolio of responsibilities continued to overlook the Arecibo Observatory. I was responsible for all facilities at the observatory. So it's been a major part of my life. So it's fun to talk about it. So really, of the 50 years of Cornell's management of the Arecibo Observatory, I've been involved in one way or another, deeply or peripherally, for about 45 of those years. I should provide you with some warning here. And the last 10 years of the observatory, when it was managed by other groups, my knowledge there is more anecdotal than it is a personal experience. But still, I think we can, I know enough to, I think, round out the story for the observatory. I don't want to, I suspect that most or many folks here already know what the observatory is, but I don't want to assume too much. So my apologies if I start to talk about some things that are blindingly obvious. I just want to start from zero in a sense and continue from there. That's the Arecibo Observatory as it was originally built. It's a 1,000-foot diameter spherical reflector, and the road you see down there is underneath the reflector. The reflector at that time was a wire mesh, so you're looking straight through it. Transparent to optical rays, reflective to radio waves. Above it, right up here is a support structure that contains the feeds for the antenna and also the receivers. The control buildings are up this road around this corner. This whole thing is supported by these three towers with bridge cables that go to the corners. This upper triangle is stationary, and this lower boat-shaped piece, arc-shaped piece, rotates in a horizontal plane. And I'll talk a little bit more about that and more specifics in a minute or two. So, question of where is this? This shouldn't surprise anyone. This is in Puerto Rico, near the town of Arecibo, which is a little, it's about 40 miles west of San Juan. When I was there as a graduate student, the major activities were a Ronrico rum distillery and a sugarcane refinery plant. The observatory itself is south of the town of Arecibo, down a very narrow, winding road. It's not on the way to anywhere, and it is really tricky to get to. So I should say it's in Puerto Rico, but why is it in Puerto Rico? And I'm going to get a little ahead of the game here, assuming that there already is the desire to build an observatory. If you're going to build an antenna with limited visibility that mostly looks straight up, then if you want to do any observing with the sun, the moon, and the planets, you need them to go within the range of view, which means they need to go more or less overhead at some time of the year. Also, this is a big structure, and you don't want wild temperature excursions because you'd like to maintain some provision, some stability. In Puerto Rico, there was an appropriately sized hole in the ground. It's in the karst region, which I'll show in other later slides. There was infrastructure, and by the way, this was a U.S. possession and was politically stable. in doing sort of reading on the background of the observatory, I discovered that there was actually a site in New York State, upstate New York, that was considered. It was eliminated because of the weather, and I would say, well, I mean, no kidding. That seemed fairly obvious to me. But anyway, the observatory has gone over time by a variety of names. It's now largely known as the Aricebo Observatory, but it also was the Arecibo Ionospheric Observatory early on. And it was also known as the National Astronomy and Ionosphere Center, NAIC, when it was being funded by NASA, which has started in the early 70s. The NAIC actually was larger than the observatory itself. It contained the observatory, that was the main activity. But in Ithaca, there was the director of NAIC, who was a faculty member at Cornell, and it was a small electronics and machining group that both developed and built receivers and receiver systems. By the way, with NAIC totally, there were about 150 people at Arecibo. Almost all of them were local Puerto Ricans. A dozen of them were probably not from Puerto Rico, from the States or from other countries. And there were probably 4 or 5 people in Ithaca in those electronics groups that I mentioned. Cornell has been managed by a variety of managers and managed for the National Science Foundation. It's been funded by the government the entire time. Cornell ran from the inception until the early 20s. Then it was the Arecibo Management Partners, and then the University of Central Florida. And you can see these 3 here in the partners and 2 other folks here in the University of Central Florida. And University of Central Florida was the last group that managed the observatory. So why was this thing built in the first place? And it all started with the thoughts of a professor of electrical engineering at Cornell, Bill Gordon, who was interested in the time of the Earth's ionosphere, in particular the Earth's upper atmosphere and ionosphere. The ionosphere had been studied for years with ionosondes, which were swept frequency radars in the HF range. And they were good up to the peak of the F2 region, which is around 300 kilometers up. But beyond that, it was impossible for those devices to measure anything in the ionosphere. So Bill wanted to do that, and he calculated that with a 1,000-foot diameter antenna and a powerful enough transmitter, he could get radar echoes from free electrons out to 1,000 or a couple of thousand kilometers. Actually, he suggested you might even get echoes from the sun. That turned out to be not true. Now, it turns out that, not so much of as an aside, his calculation was almost right, but not quite. And after he published this paper, this is in 1958, I think, a former Cornell student, then I think working for a National Research Lab, Ken Bowles, did an experiment in his institution, and with a small antenna, managed to get a substantial echo from the upper ionosphere. Turns out that the scatter was not necessarily incoherent, but the electrons were acting more in concert than had been anticipated. caused largely by the presence of the heavy ions up there. So there was a much stronger and narrower signal than Bill had calculated. So with that, in fact, the question is, well, do you really need a 1,000-foot antenna? But they went ahead with the antenna anyway, even though they knew that it was probably not necessary, because there were other things going on in the environment, both the political and scientific environment in the late 50s. One was, as I just mentioned, Bill Gordon's interest in the ionosphere. The other was Sputnik 1 and Sputnik 2 had gone up and shocked the U.S. populace by being first into space, and then the U.S. launched Explorer. So there was a lot of interest in the upper atmosphere. The Van Allen belts were discovered by Explorer. That's radiation belts high in the ionosphere. And there was also interest in being able to detect ICBM atmospheric entry trails, and an interest in potentially being able to understand or to detect high altitude nuclear tests. The issue of the ICBM atmospheric trails had an unexpected consequence, and that is that somehow that word got around in local Puerto Rico. So some folks took that as the purpose of the Arecibo Observatory was, in fact, a redirect incoming missiles from the States to Puerto Rico, which was nonsense, of course, but that didn't matter. And there was some concern that the observatory would be under siege if by these folks. Turned out not to have been a serious matter, but it was something that was sort of top of mind most of the time. But at any rate, in that environment, the Advanced Research Projects Agency, which is now DARPA, funded the proposal for a 1,000-foot diameter reflector with an 870-foot radius of curvature and a 20-degree swing from the vertical. That is, you could steer the beam of this thing 20 degrees from the vertical. And that was 1959. So where did the 20 degrees come from? Well, I will get to that in a moment. The proposed observational modes of the observatory at that time was the incoherence backscatter from the ionosphere, which is what I was just describing, a radio astronomy, which is a passive observations of the cosmology of cosmos, and radar astronomy, which is sort of straightforward radar studies of the moon and planets. Maybe I ought to say something about radio astronomy, just to put that into context, because in fact that's what the observatory spent most of its time doing. Radio astronomy, or radio emissions from the cosmos, was first discovered by Carl Jansky at Bell Labs in Holmdel in 1931, and he was really looking at noise sources, studying the direction of thunderstorm static. And then Greg Reber picked that up several years later, 6 years later, and with his own backyard antenna, did a radio map, the first radio map of the radio sky, and we found a lot of sources there. Now, I should say, as an adjunct to this, sort of 30 plus or minus years after Carl Jansky, two guys at Bell Labs, again, at Holmdel, were trying to understand the noise from a horn antenna that was typically used in communication systems in the Bell system. And they found that there was this unexplained noise that was the equivalent of radiation from a black body at 3 degrees Kelvin. What they had discovered was the redshifted remnant of the Big Bang that created our universe. For that, they won the Nobel Prize in 1964. That was just, I mean, such a profound discovery that it changed and continues to change thinking about cosmology and the evolution of our universe for all time since. It was an enormous discovery, and trying to put your finger on that small amount of noise is no small deal. Anyway, so that's radio astronomy. Now, in radar astronomy, you got to remember that light has a finite speed, and it takes a while for, say, a radar beam to reach the moon and come back. That's only 2.6 seconds. But if you want to study Jupiter or Saturn, and Jupiter is a little over 6 hours round trip, and Saturn is 2 hours round trip. Well, the Earth rotates for 15 degrees per hour, so figure out how long you have to point at an object. The 40-degree steerability, that is 20 degrees on either side of the vertical, provides a 2 hour and 40-minute track time, which is just enough to do a little bit with Saturn and Saturn's rings. And Arecibo has been successful in doing radar studies of Saturn and Saturn's moons. This is a telescope, as I mentioned before, with a stationary suspension structure here. You see these small cables coming down here. They're over here as well. Are what are called tie-down cables, and they provide torsional stability, but they also provide some temperature compensation. That is, when the temperature goes up, these large suspension cables will expand, but on the other hand, these tie-down cables, which are under tension, will also expand. So the platform will want to sink, but these will release their tension and allow it to go back up. It's not perfectly temperature compensating, but it's close. This is a catwalk on which you can walk from the ground over here up to the telescope. That's one of two ways to get up there. The other is a cable car, which you can't see here. And of course, this thing is suspended from 3 towers. These two are, I think, several hundred feet tall. This one is about 100 feet taller. The tops are all at the same level, but the bottoms start at a different elevation. And you can see the terrain in the background. It is all vertical here, full of limestone sinkholes. This is seen from the top of the Tower 12. The 3 towers are designated according to the clock face. T12 is the one on north, and then it's T4 and T8. The suspension of the main of the triangle here is 4 of these 4.25, 4.5 inch bridge strands, each of which has got about 160 individual wires in it. And these things are absolutely critical. I mean, stating the obvious. So there was a lot of attention when Corner was running this, a lot of attention given to the condition of these cables. This is a view of the more directly overhead of the reflector through which you can see. The reflector is held in shape by these major cables running north-south about every 100 feet. But what you can't see is orthogonal to them are the lighter cables, more closely spaced, run east-west, and they then support the mesh that you're now able to see through. Up in here is the operation. This is a receiver room and a control room, an office building, and some support services back here. This is looking through the mesh. I think this was called hardware cloth. The openings are about a half an inch, plus or minus. And this, I'm a little ahead of the game here, but this is a vision of a view of the support cables. These are the main support cables, and then they are attached to tie downs to concrete blocks set on the ground here. And there is tension applied to each of these cables to force them into a spherical shape. They will, if just hanging on their own, they will be in a catenary, not in the proper shape. But with the tie downs are used to pull them into proper shape. That's kind of a tricky operation because this is like a fabric, and you pull down on one of these, and it affects things that are close to it. So there's an iterative process that has to go on. This is the catwalk before it's completed. When it was completed, it had chain link fence on either side that went up about 5 feet. But these wooden planks remained, and I will tell you from personal experience that walking up this catwalk is not for the faint of heart. It is a really scary business, and all the time I was there, I was never able to successfully encourage a visitor to go up the catwalk. If they wanted to go to the suspended structure, you would go up in the cable car. The advantage of the cable car was it was no less scary, but when you got in the cable car, you shut the door, you were surrounded at sort of shoulder height by a steel cage. You pushed a button on the cable car building, and then you were on your way, and there were no controls in the cable car, so you were just going to the top of the suspended structure, whether you wanted to be there or not. It was an adventure. This is a receiver room in the operations building, and there's some in the background here is a control room where you would control the position of the telescope itself. But in here were the guts of the signal processing equipment. Now, the receivers themselves were located up on the suspended structure right on top of the feeds. Everything was converted to 30 megahertz and then sent down to this area, I think right in here, at 30 megahertz. And then it was followed by all of this various signal processing equipment, operational amplifiers, filters, whatever. And there was also an analog to digital converter, which is, I think, I recall, was over in here. It was connected to a computer which was state of the art at the time, but you would consider it extremely primitive by today's standards anyway. Another kind of fuzzy view of the same thing. So when an experimenter came and did an experiment using the telescope, they would have a receiver configuration in mind, and they would set that up connecting to each of the various signal processing elements by these coaxial cables. Every experimenter had a different setup. So we had telescope operators, and this is a good friend, Angel Vasquez, who some of you may know, very active ham radio operator now from Puerto Rico. But anyway, he was a telescope operator at that time, stayed with the observatory right through to the end, and was a senior member of the administration there toward the end. But anyway, he and his colleagues would help set this thing up for the experimenters, and then it would take it down, and the next person would come in, and they set up something entirely different, perhaps, and so on. That went through the day, 24 hours a day, 7 days a week. Um, and so the implication there is that there are lots of people using the telescope, not simultaneously, but sequentially through the day, which means there needs to be support for folks who are maybe visiting from the States or elsewhere around the world. And so the observatory also had what we call visiting scientist quarters. This is one, this is what's called a family unit. There were two of these. This was a two-bedroom unit. And interestingly, it was patterned after a resort home on Culebra Island, which is a small island between Puerto Rico and Virgin Islands. There were four bachelor units, sort of in this mode, and then six motel type units. And they were pretty heavily used actually by visitors. And of course, we're in Puerto Rico and it's hot, so you gotta have a swimming pool and a volleyball court. And the volleyball court in particular was heavily used by the staff at lunchtime. So, as I mentioned, this is a spherical reflector, not a parabolic reflector, but the parabolic reflector collecting the energy or feeding the antenna is fairly straightforward because all of the rays come together in a single point. With a spherical reflector, that's not the case. And these are ray tracing for a spherical reflector of the parameters of Arecibo. And you can see that the ray coming from 500 feet away, that's that one, sort of the radius of the Arecibo telescope, crosses down here at about 96 feet below what was called the paraxial focus. If you want to illuminate a smaller area, say 750 feet or 700 feet, you would have to have something that's 40 feet long and so forth. And you get the point. The things don't come together at a single point, but over a line or a surface up here. So that makes it tricky. Furthermore, if you look at this diagram, is an example of what would happen, what does happen when you steer the antenna and move the paraxial focus in this direction. The illumination moves up this way, and if the illumination is a full 1,000 feet, that is the full 1,000 feet this way, that means the illumination suddenly immediately begins to fall off the edge of the dish and look at the ground. That means the gain goes down, the beam shape changes a little bit, and the noise temperature goes up because the ground is way hotter than anything you're looking at in the sky. So that was the challenge of how to feed the Arecibo telescope, and it remained a challenge right through the end, honestly. So this is a 430 megahertz line feed. It's a slotted waveguide of a very specific design. It's 96 feet long. This is a technician doing, I have no idea what, because there are no moving parts down here, although birds occasionally like to hang out here. Like an upside down ship mast with spreaders and shrouds. And that's attached to the carriage house up here, which is where the receivers are located, and also where the turnstile junction for the transmitter is located. That takes the power from the transmitter, puts it down this feed, but when the signal is being received, the turnstile junction sends it to the receiver. This is a start of the alternative way to put more feeds up there. This is still a 430 megahertz feed. This is a 40-foot feed that's probably feeding about 700 feet. And it's at a different frequency. I think this one's at 318 megahertz, so I'm not positive of that. And things just totally began to get out of hand This is now this is after the first upgrading, but the principle is the same. This is a carriage house. Now, these are more line feeds. I'll show another slide of those from the side. But if you don't want to build a line feed, with some compromise, you can feed the antenna with a Yagi array, which placed in the right place with the right beam shape will work out okay. This is that same arrangement. Here we've got 5. This turns out to be 21 centimeter feeds, and another 5 of them over here. They're all slightly displaced, so they're able to sweep a beam of 10 beams simultaneously across the sky. And then there are these other Yagi feeds at different frequencies. I'm not sure what frequencies they are, but typically we were using Yagi feeds at 73 megahertz, 110 megahertz, 318 occasionally, and all the way up to about 611. So before the first upgrading, and early on, this is the kind of stuff that went on. The atmospheric studies were really very successful and did very much what Bill Gordon had hoped they would do. Planetary radar discovered that the Mercury, the rotation rate of Mercury that had been expected was wrong, and they found the correct rotation rate. They found that Venus rotated in the wrong direction very slowly. I should say Venus, the planet Venus, is shrouded in a dense, opaque, visually opaque cloud of carbon dioxide. It's impossible to see the surface. It's virtually impossible to tell how the planet is rotating, and it's impossible to tell what the terrain looks like. And it has a ferocious greenhouse gas effect, so that the surface of Venus is about the temperature of the melting point of lead. It's a tough place to visit, and I'm not sure, I've kind of lost track, but I'm not sure we have yet been successful in sending a spacecraft to the surface of Venus. Several have tried and have passed away on the way through the atmosphere. Anyway, early maps of the surface of Venus were done. There was also a radar map done of the moon, and then there were passive observations of planets. Venus, I was, as a graduate student, was doing some observations of Venus, various nebulae, quasars, supernovae, sort of the smorgasbord of celestial objects. And then there was the observations of newly discovered pulsars, and the search for and discovery of more of those. I should say something, well, like also radio occultation observations. Radio occultations is an interesting business. You track a object on the sky and watch how its intensity varies as the moon moves in front of it, that is, occults it. And you are able to measure the diffraction pattern of the radiation from that source, which then gives you some information on the size and possibly the shape of that object. And at that time, we were trying to understand what quasars were all about, and thought they were maybe a very small source of point source. So for pulsars were discovered by a graduate student, Joycelyn Bell, in England in 1967. And what she discovered were pulses of energy that came at a very regular interval from early on from 4 places in the sky. The interval between those pulses varied from source to source, but for a specific source, the intervals were totally regular. Turns out that Arecibo was really well suited for these kinds of observations. First of all, it had greater sensitivity, signal to noise than virtually any other telescope in the world. And we had radar equipment, which meant that we were accustomed to dealing with pulse signals. So with analog to digital converters and a computer behind it, we were able to really study these objects, newly formed objects, very well. And they are thought to be remnants of a pulsar is thought to be the remnant of the explosion of a star. This is a Crab Nebula, a star that exploded in 1054 AD. It was witnessed by the Chinese and recorded by the Chinese. It has within it a pulsar that is pulsing every 33 milliseconds. I'm not sure which of these. I think this was a star right here, but it could be one of the others nearby. This happens when a star runs out of its fuel. It begins to collapse inward, and then in the collapsing heats up and eventually it blows off the outer layers of the star, with the remnant being either a white dwarf, a neutron star, or a black hole, depending upon how much stuff is left. A neutron star is something that probably is the total mass of our sun, but the size of about Manhattan or Los Angeles, say. Spinning at 33 milliseconds per rotation. That is, they are really spinning. It's totally neutron material, extremely dense, and it has to be dense with great gravitation in order to stay together when it's rotating at that speed. By the way, this stuff out here is all heavier elements that then will be dispersed into, and by heavier elements, I mean carbon, hydrogen, oxygen, and so forth, beryllium. And that will be dispersed into the cosmos, will mix with the cosmos, and then it will likely collapse with other material into yet another star. This is where we come from. This stuff is, as Carl Sagan would call it, stardust, and we are all made of stardust. The heavy elements that are make us up and our world up, all were created in a star at some point in a star explosion somewhere prior to the formation of our own star. Now so the discovery of pulsars garnered Joycelyn Bell's PhD advisor and another colleague at the Cavendish Lab in England a Nobel Prize. Joycelyn did not get a Nobel Prize, and it's been really controversial. I will say I know Joycelyn, and she is one of the most gracious folks imaginable, and seems to be unperturbed by this. What seemed to others of us in the business as real slight. I'll only talk about two pulsars. One kind of a silly result, and the other one way more profound. I was mentioning before, one of the things that I did as a graduate student there, I was looking to see if there was any particular pattern to the shape of the pulsar. Was there any correlation from one pulse to the next pulse to the next pulse? So this is a compilation of, I think, 80 to 100 pulses. Time goes from bottom to top and from left to right. The pulse itself looks like about 40 milliseconds long. And my conclusion was that there was no there was no correlation from pulse to pulse. This appeared in my thesis, and I thought that was the end of the deal. And it was, to my surprise, several years later, when a friend of mine pointed out that this image from my thesis appeared on the cover of the album Joy Division, Unknown Pleasures. I have no idea how it got released into the public and how it happened here, but this has become a pop icon, and you can. This is from Amazon. You can buy a T-shirt with this on. Actually, one of my sons has one of these, and so does one of my granddaughters. And I've seen my wife has a piece of jewelry that has this thing on it, and I've seen pictures of a gentleman who had his back tattooed with this. So apparently, particularly in England, it is really quite widespread. And there is no science involved in this at all, but I would say this has probably got greater publicity than the much more important discovery that was done a little bit later. So in the late 60s, it was recognized that Arecibo had its limitations and its opportunities. One was that it was hoped that we'd have a much more smooth reflector surface to allow observation at higher frequencies at 1420 megahertz, which was a very important emission line from hydrogen atoms. We also wanted much easier multi-frequency operation at those higher frequencies, all frequencies really, but at higher frequencies too. This follows on my demonstration of all those sort of Rube Goldberg feed arrangements. A higher power transmitter for radar studies, planetary studies, and a ground screen to reduce that system noise from vignetting. That is when the feed antenna beam falls off on the ground. So what was done? Well, we didn't get all of the desires, but there was a new reflector surface that was put together with 38,778 aluminum panels. The S-band radar system was installed of 500 kilowatts. It was originally thought to be a megawatt. I was the project manager on the S-band radar system. We had hoped it would be a megawatt, but we couldn't afford it, so it turned out to be 500 kilowatts at 2380 megahertz, and we built a 40-foot line feed that was feeding 700 feet for that. We had to put an auxiliary power supply for the transmitter because the grid couldn't handle it. And we stabilized just slightly the suspended structure, and there was a new carriage house that was put up to support feeds. And this is an image of the new feed going in, and the new surface going in. The new surface is over here. The old surface here. That's the last panel going in. Now the association has two panels like this, one dirty, one clean, in the very fine exhibit in the museum. The light that reached the ground changed dramatically with that new surface, so that the ferns underneath the dish really liked it. This became a beautiful fern garden, and you can see the array of tie downs here that were used to fair the dish. There's a workman on the dish using sort of snowshoes, except not snowshoes, to distribute the weight. And he's placing on here targets for a laser measuring system to set the reflector. The individual panels were connected to the support structure by this screw structure here, which allowed someone from underneath to lift or lower the corner of the panel. This rusted U-bolt was another problem that had to be resolved. this is the platform from underneath that would allow the workman to adjust the screw to adjust the panel position. This is a lift of the new carriage house too, and you can see these arrays of surveying targets. These targets the service was set by surveying at night, illuminating the targets with big searchlights, which of course we should have anticipated that one evening the operators of the searchlights thought it would be fun to illuminate a passing by commercial airliner was flying from the west end of Puerto Rico to San Juan. You can see the reflector here, and I want to point out that this is really bright. And one of the effects that we discovered almost immediately was that, as I mentioned, the sun goes directly overhead in Puerto Rico, which means that all of this energy is focused somewhere up here, which means people working up here, it was really bright and really warm. And the first complaint I got when I arrived there as the director was it was too warm to work up there. And one guy told me he was getting sunburn on the inside of his nose, which I think was nonsense, but I got the point. On the other hand, this is a problem that fortunately solved itself because by the time spring came around the next year, the surface had oxidized enough so that the reflection was still there, but not as bright. The dedication of this was an opportunity when we sent the Arecibo message out. I won't dwell on this. I think in the display at the museum, this is well explained. This was sent with our 2380 megahertz system. Probably was the brightest man-made emission from Earth ever. Was sent to a cluster of stars 25,000 light years away. The chance that this will be received by anyone in that cluster is vanishingly small. The chance that they would respond is even more remote. If they did, it would return to us 50,000 years from now, would potentially be received by whatever or whomever happens to be there. At that time, I should point out that 50,000 years ago was when modern humans in perhaps the second or third wave were settling in Europe and mixing it up literally with Neanderthals. So things will be different 50,000 years from now. But at any rate, that was part of the dedication ceremony. And although some of us who put this together thought this was a little hokey, in fact, it was quite a moving experience. I will say, even though I knew exactly what was going on, even I was somewhat moved by how it all worked. And I was surprised to see that when we started transmitting, and it was this warbling tone that was transmitted to the gathering area, virtually everybody got up out of their chairs and walked over and looked at the observatory and looked up at the sky. So with the new surface, we began to develop now much better surface maps of the surface of Venus. This is from my friend Don Campbell. His maps, you can see structure here, which means that Venus has tectonic activity like we do. There are craters here which surprised me personally because the atmosphere is so thick. It had to be a big object to make it through that. We also did 21 centimeter surveys of the galaxy and of the Milky Way and other galaxies. There was some sporadic searches for extraterrestrial life. And then there was the discovery of the binary pulsar, which was first discovered, and then examinations of its timing showed that it indeed was a pulsar. It was in orbit around the second neutron star, both of them about 1.4 solar masses. And there was a high gravitational environment, and you would expect gravitational radiation and orbital decay as a result of that. And that resulted in the results from Joe Taylor and Russ Hulse showing the residuals really of the timing, and compared with Einstein's general relativity prediction, you can see the error bars are almost too small to see here. This confirmed Einstein's general relativity predictions and Einstein's theory. So this is a tremendous discovery and confirmation. It got Joe Taylor and his graduate student, in this case, Nobel Prize in 1993. And as Mark and I were talking earlier, this Joe Taylor is known to ham radio operators as the Joe Taylor K1JT, who produced the WSJT X transmission technique in FT8. So that was the pulsar activity that really mattered. I should say, as an aside, Arecibo has been the site for a couple of movies. If you saw GoldenEye, a James Bond movie with James Brosnan, that was one of them. They're running around what those of us who were at the observatory used as a jogging track, 1 kilometer around. The other movie was a movie Contact with Jodie Foster, which was in a way, it was written by Carl Sagan, but patterned after Jill Tarter, who for many years ran the SETI Institute in Pasadena. So still, we want to upgrade even further, and I'm going to move quickly here. Second upgrade was the ground screen Gregorian feed with a radome and other miscellaneous adjustments. This is where the Gregorian feed works, and this is ray optics. This is a sort of a 3-cushion shot. Comes off the main reflector, off of the secondary reflector, off a tertiary reflector, and then to a focal point here. And this will be in the carriage house where all the receivers are. So that was put together, and this is the picture of the radome around that array of antennas, and how it looks with that radome installed. Now, this is personal opinions now that are going to follow. In my opinion, this scientifically and technically was really a success. It worked wonderfully. Aesthetically, it changed the balance in my eye of the telescope. This is the catwalk, by the way, that we're seeing here. But also, and this is my opinion, it made the telescope a bit more vulnerable to natural forces. There were obviously more windage here, rather substantially. And because we're now operating at higher frequencies, the telescope had to become stiffer so that the accuracy of pointing would not degrade. And the telescope took a couple of hits. Hurricane Irene in 2011, Irma in September, and Maria also in September, 2 weeks later. And then there were a series of earthquakes in December of 2019 and also in January 2020. All of those had to have put shocks into the suspension system, And in August of 2020, one of the auxiliary cables, the upgrading to maintain this extra weight had added 2 extra cables to each one of the towers, and one of those cables pulled out of its socket. That clearly was code red. And then they were reporting that there were about 1 wire per day was breaking, or 160 per cable. So that's another clear warning signal. And in November of 2020, the support cable snapped. One of the main support cables snapped. It was too dangerous to try to repair the telescope. You notice there should be a cable right here. This is the cable that failed. The main suspension cable that failed. So that was the end of the Arecibo telescope. And in the spring, Angel Vasquez, my friend, went up to the observatory and took a couple of pictures. And this is what it looked like in the spring of this year. So now what? In the 80s, there was constructed at the observatory a visitor center and science center. As you see here, rather quite nice structure constructed with the help of the Angel Ramos Foundation. I think a little money from Cornell, from University of Puerto Rico. So that is now being proposed to be used as an educational center called the NSF Arecibo C3. This is where the C3 comes from. It's supposed to open in November of this year, being operated by these 4 organizations. So something will be happening there, which is reassuring. But still, as far as I was concerned, that is the end of an era. And although it pains me to watch the collapse of the telescope, I like to remember it as it is here, when it was in full operation, or as I saw it on my first approach in 1967 as a graduate student from the approach road.